All right, good morning, good afternoon, good evening, depending on the time in which you are choosing to watch these series of videos. Welcome back to another segment of climate. So we are going to discuss some things like natural causes of climate change, as well as getting into how we measure previous climates. And if we can get into it, depending on the length of these videos, some impacts of climate change and kind of where we're going from here. So the big thing and big announcements for this week include, since we're starting to kind of wrap all this stuff up, we are approaching quite quickly our next exam. So your second exam is going to be available next week. Same format as the previous exam, perhaps though a bit longer because there is one more chapter compared to the other chapters, or to the previous exam, which was only 3 chapters long. So the big thing here is that your SmartBook reading assignments are due on Sunday. So please make sure that you are working through those and shipping those away. Do not leave those for the last minute. You will not be happy with me, or you will not be happy with yourselves. And that's not my fault, right? I've been reminding us every single day that we've been meeting that is a thing. The second big announcement is if you have not yet turned in your rough draft for your peer review, please do so as soon as possible. I know that there's kind of some time between when you turn in the rough draft and then, of course, when your final draft is due, but there's spring break in between that as well. So just kind of keeping those things in mind, and then you won't be assigned a peer review person until you turn in a version of your own. If you've already turned in a rough draft, awesome. Thank you so much. If not, please do so as soon as possible. All right. Please reach out if you have any questions, comments, or concerns on those ideas. But let's go ahead and get on into it, shall we? So, what we ended with on Thursday was kind of asking us about natural ways in which the climate has changed, right? And we kind of came up with 4 main ways. First being solar intensity, variations in solar intensity, right? The big idea here is if the sun is emitting more energy, then we would have more energy reaching here to our surface of the earth. The biggest one is actually going to be the changes in Earth's orbit, and this is called the Milankovitch cycle. Next will be volcanic activity, which is actually a global cooling effect. And then the last is plate tectonic activity. And we talked at length about plate tectonics throughout the beginning of the semester, so I'm not going to go into a whole lot of detail with that. I'll just kind of mention what could cause some various changes in climates around the world. So first thing we're going to start with is solar variability. So the idea here, again, is pretty simple. So the more solar output there is, the more warming we would have here on Earth. Unfortunately, we don't have enough data to back up this hypothesis, right? We weren't around 800,000 plus years ago, and what we can see in our natural recorders of climate can't really tell us exactly what was going on with the sun. We can, of course, have hypotheses, and we can have some information to back this stuff up, but with good hard evidence, technology just wasn't available until 1979, and we need more decades of data in order to get a better understanding of how the sun could have impacted our Earth, temperatures here on Earth. We know that there is, the sun does go through cycles. There's an 11-year cycle. There's even a 27-day cycle. You know, everything in the universe has cycles, whether we like it or not. Male identifying folks, do you have cycles too? Women, of course, we know we have cycles as well, right? So everything in life has a cycle. Everything in the universe has a cycle. There's always a beginning and an end to everything. There's, I said that everything is always waves, right? There's always ups and downs. Same thing goes for all things in the universe. So another working theory with sun variability is sunspot activity. That's the 11-year cycle, when the solar output is at its maximum, and it's only slightly more solar output, right? And this appears that this cycle has a very small impact, and there's really not an appreciable change in temperature here at the surface. But there could be long-term variations in solar output that could indeed have an impact. Again, we just don't have like a super solid, yes, this is happening sort of thing. I will also point out that solar variability is an aspect that I looked at in my grad school work, actually. So we looked at solar minimum and solar maximum, and like the difference between solar minimum and solar maximum is like maybe maybe 2 watts per meter squared. It's such a small variation. It's really quite wild, but it's a very clear oscillation. We'll actually see in our next slide here. So this graph here is looking at temperature versus solar activity. So the years are on the x-axis, solar irradiance, so total solar sunlight basically is a way to think about that, is on the left y-axis, and Celsius is on the right y-axis, temperature being the red line and solar being the yellow line. So we can really nicely see this 11-year cycle, right? This really clear up and down motion, which I think is really fascinating. The other big takeaway that I can get from this is, yes, in the early 1900s, we can see a pretty nice correlation between the two, right? Where the temperature is increasing, hey, guess what? So is the solar variability. Is it necessarily equal? Not really, right? We kind of see this pause in temperature increasing, but then we see after about like the 1970s-ish a pretty stark increase in temperature, whereas the solar irradiance or solar energy is decreasing, right? It's a very, very stark kind of separation between the two after about the 1970s. And this is also a really small cycle, right? This isn't something that takes thousands of years to correct or to balance itself out. This is a very quick cycle. So we need to look at something that takes longer. And with that, we're going to get to variations in Earth's orbit. So this is called the Milankovitch cycle. So this guy out of Serbia, Milutin Milankovic, created this hypothesis, and he also created a comprehensive mathematical model that is based on the following elements. The first is eccentricity. So that happens on a scale of 400,000 to 100,000 years. And we can see that our diameter of our orbit has shifted, right? We haven't always been the really nice ellipse that we have now. We've actually been closer to the sun at times, or even further away from the sun at times. The next is obliquity. So obliquity happens on the order of about 41,000 years. So that's a much faster cycle than the eccentricity one. And this is basically that we wobble, right? We wobble. Our axis shifts, right? We're not always at 23.5 degrees. It actually turns out that with the really, really large earthquakes, we kind of go a little bit further off our 23.5 degree axis, which is really quite fascinating. And then the last one here is axial precession, and this happens on the order of 23,000 years. So the idea here is that like in our summertime in the Northern Hemisphere right now, in our summer, the Northern Hemisphere is facing the sun, right? Or we're starting to face the sun. We're going into spring and summer, right? Whereas the Southern Hemisphere is facing away from the sun. Well, the idea with axial precession is that the opposite has been true, where when we know summertime in the Northern Hemisphere, like June, July, August, has actually been wintertime temperatures. So it's been like a variation in seasons, which is really quite fascinating. So these factors cause little to no variation in total solar energy reaching the ground, right? So the amount of sunlight that's reaching the ground has not changed. But the idea is that parts of the Earth have been, have had more of a direct sunlight, right? And so the impact here is felt in the contrast of seasons, which could mean milder winters in the mid to high latitudes. So like where we're at all the way up to the poles. And then greater snowfall total and cooler summers bring reduction in snowmelt. And these theories are really nicely backed up in sea sediment data. So this is kind of like the main idea we believe that climate has changed in the past. Some other things, some other kind of internal forces that can change the climate would be volcanic activity. And so with volcanic activity, this one's really fascinating, I think. So when volcanoes erupt, they have this huge influx of sulfur dioxide in the atmosphere, which cools the atmosphere actually by reflecting incoming solar radiation. So it acts as like a big shield in a way. So the sun's trying to come in and sulfur dioxide is like, no, I will shield you. And we're like, oh, thank you so much. This is so nice. This is really only a short-term change, but it is a very considerable one. And this is also the basis for the argument for albedo modification in order to combat climate change. So that's what this graph here is trying to show, the short-term change, right? So this is years on the x-axis and global temperature anomaly on the y-axis. And we can see after some of these really large volcanic eruptions that right after there's this huge kind of downtick in global temperatures. But that doesn't mean that global warming has stopped, right? So we can still see a very clear and steady increase even after these large eruptions. So the big problem, I think, with albedo modification in order to combat climate change is that it's something that would have to continuously happen, right? We would have to continuously inject the atmosphere with molecules that are potentially unnatural. We wouldn't know the overall impact of that. There's like a whole myriad of reasons as to why this would probably not be the best thing to try and do. There have been folks out there, maybe you've seen these headlines of like startup companies that are just like doing it, which is not the right way to go about this. Like, I understand the idea of wanting to just pull yourself up by the bootstraps and just freaking do it, but there's reason why there's science in the mix. Like we care about experiments and making sure that things are actually safe, right? That's a big deal. So the last thing I want to touch on is plate tectonics, right? We talked a lot about plate tectonics, just remembering what it is, right? So it's the idea that these crustal plates are moving on top of the asthenosphere. And this helps explain why glacial activity is seen in present-day warm areas, right? That was one big thing that Alfred Wegener had to say about it. And what's really fascinating is these plate movements also likely altered ocean currents. I mean, that makes sense, right? Water or land gets in the way of water movement. And so that could also alter the climate. So, for example, like if we look here where Pangaea, we believe was, North America is like at the equator, right? So we would maybe have some warmer waters and some warmer temperatures observed here. Same thing with northern Eurasia. But then as things have separated, the global circulations that we would see are now much different, and they can impact climate in various regions. I mean, the East Coast tends to be much warmer than the West Coast because the ocean next to the East Coast is warmer than the ocean next to the West Coast. So we know that the ocean has a very huge impact on local climate variability, and that's a pretty interesting thing there. All right, so that's it in terms of natural variation, external natural variation, internal natural variation. There, of course, are other things. Like if we add humans a little bit into the mix, in terms of like volcanic activity, you could concern yourself with like aerosol loading, so nuclear bombs or fires, right? If you ever notice when we have a big fire and there's a lot of smoke in the air, it might be cooler that day. There's something that's not a cycle, but of course something that will obviously alter the climate would be, of course, asteroid hits, right? So there's a reason why the dinosaurs are not here walking around with us, because they were exterminated by an asteroid. But that is something that is completely external that we don't have. That's not like a normal cycle thing. So just keeping all those things in mind. And with that, thank you so much for your time and attention. And I will see you in just a little bit talking about how we measure all these previous climates. Thanks.